Okay, this is an example using the loop laws and the junction laws. And it's reasonably complicated. We have all these resistors. We have two batteries. And you can see we go from negative to positive, 12 volts across this battery. And we go from -4 to, well, from negative to positive. The difference is 4 volts at this point. So what I'm going to do with this is I'm going to use the same figure, and we're going to do the junction law first. Now, even before that, we have to, so before we use that, let's go back to the original drawing, and we have to assume the direction for currents, and we have to name them. So I'm going to call this current 1, and I'm assuming it's moving in this direction. Okay, so that also comes into here, so this is also I1. Okay, we come to a junction, so there's going to be I2 this direction. I'm going to assume that I3 goes down like that. So I2 comes over here, so you've got I2 here, you've got I2, these are currents, and you've got I2. Because there's no junctions at this point, we're just connecting elements. Okay, I3 comes down here. We have I4 going this way, and then we have, so this is another junction. So let's label the junctions with red. So that's a junction, that's a junction, that is a junction, and that is a junction. Okay, so we have 4 junctions. It's fairly complicated, so hopefully I can explain this to you. Okay, so you got current 3 coming here, current 4 going that way, current 5 coming out of the junction. We've got current 2 going in here. So the current, we're assuming it's going this way. If we guess wrong, we'll find out. Okay, the current 5 comes down here, goes into this junction, and then we have current 6. And current 6 goes through there. So we have current 6 coming in, and we have current 1 going out, and we have current 4 going in. So you see we have 6 unknowns, I1 through I6. So again, until we come to a junction, the current is the same value. So we have I1, I1, I1. Here we have a junction. I2 comes out, goes down all the way around to here. I3 comes down to this junction. I4 goes to the left. I5 goes down. I5 also comes in here as well. So let's just move that down so we can see all these things happening. Okay, so we have I5. Okay, so those are the junctions, which I guess I've already done over here. So 1, 2, 3, 4, 5, 4 junctions. Okay, so what does that mean? Well, we look at each one separately. Let's call this junction A, call this junction B, junction C, and junction D. So for junction A, this one right here, we have I1 coming in, so that's positive. I mean I6 coming in. We have I4 coming in, and we have I1 leaving, and that all has to equal 0. Okay, junction B, we have I1 coming in, I2 and I3 going out. If we guess right, then they'll all be positive. If we guess wrong, then it'll end up being negative. Okay, so that's junction B. Junction C, we have I3 coming down, so let's write that down here, I3. So I3 comes in, and I4 and I5 go out. So we have I3 minus I4 minus I5 equals 0. And then our final junction is this one down here. We have I5 and I2 going in. And I6 going out. Okay, so we have 4 junction rules. That means we need 2 loops because we need 6 equations and 6 unknowns to be able to solve the problem. And we're going to solve it using our graphing calculator. So adding extra complexity doesn't make solving the problem that much more difficult. You just have to keep track of everything. Okay, so those are the junctions. The loops, here's the loop. So we can pick any one of these two. And I think we want to include the battery in at least one of them. So we're going to make that one loop, and I'm going to make this another loop. And I'm hesitating. It seems like I need one more loop, but I don't think I do. You do definitely want to include the batteries. But notice I don't have the 6 ohms in there, which is bothering me here. So let me make sure I haven't forgotten something. Is there any other currents that I need to remember? 1, 2, 3, 4, 5, 6. Okay, so 6 currents. Is there any redundancy? Don't see any. Redundancy just means I have the same currents involved in the same equations, but these are all different. So that should be all that's required. I'm going to pause for just a second and think about this. Okay, well, I've just been in the book, and it says, apply the junction rule to any junction in the circuit. The rule may be applied as many times as a new current, one not used in a previously found equation appears in the resulting equation. So that's why it seemed like I had, I used too many here, because you can see, let's just list the currents. So we have 6 currents. I'm going to list these down, and then we'll mark them off as we use them in equation. So in this one, I've got I6, I've got I4, and I've got I1. Okay. This next one uses I1 and I3, and I2, I1, I2, I3. So all we got left is I5. So we could use either one of these. I'm going to choose the third one. So this one uses I3, I4, and I5. I've already done marked out that, and I've marked out that, marked out that. So we don't need to use that one. That's a redundant current result. So now I have 3 equations and 6 unknowns. So I need 3 loops, and you have to make sure you include everything in the loop. So these 3 separate loops cover every element. I wouldn't want to do this as a loop, this is a loop, and then do this as a loop, because I'd leave out these 3 things. So the way it works is you look at the voltage change, and let's just write it down here. For the resistors, the voltage is equal to the current times the resistance. So again, going back to through this resistor I have I1, let me make sure I got these right. So bounce back here. So I'm going to write down what currents are going through each element, especially the resistors. Okay, so this had I3, this had I4, this had I5, and this had I6. So I've taken all the resistors and I put the corresponding currents that have to go through those. Make sure I got those all right. I4. So this is I4. I do a very good job drawing it. This is I4. I5 is coming down. I6 is going across. Okay. So now what we do is we look at these 3 loops. That'll give us 3 or more equations. So let's go. You just pick some point in the loop. So I'm going to pick that point. So we have plus 12 volts going from here to here. But the current, the other thing you have to do is show which direction you're assuming the current is going. So it's going that way. I assume that was going that way. This was going this way. This was going that way. This was going that way. This was going this way. And this was going that way. So if you're going in the same direction as the current, then you have the voltage drop. If your loop goes the opposite direction, then you have a voltage rise. So this is going to be a voltage drop. So the voltage is equal to the current times the resistance. And I'm not going to put the units in because it gets too complicated. Okay, so that's that. Loop around here. Then we have plus I3 times 1 ohm, going in the same direction as my assumed current, plus 2, or actually I4 times 2 equals 0. So that is this loop. Let's give them some names. We'll call this loop F, G, and H. So this is for loop F. Okay, for loop G, let's pick any point, doesn't matter where you pick. And you can go clockwise or counterclockwise. I'm just going to go clockwise as a kind of a convention. Okay, the current's going in the same direction as I'm looping. So that means I have a voltage drop. And so that, I should have had all these negative up here. I don't know why I did that. This should be negative voltage drops. So basically what it's saying is you have voltage rise, drop, 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 and then you're back to start over again. Okay, so here we have a voltage drop, which is going to be negative I2 times 5. Then we have a voltage rise of 4 volts across the battery. Then we have a voltage drop across that. And so voltage is current times resistance. And then we come up this way. But notice we're going opposite direction. So in this case, it's going to be plus I5 times 1 ohm. And then we go through this one. Again, we're going the opposite direction. Our loop is going the opposite direction than the assumed current. So we have plus I3 times 1. And that equals 0. And then we have a loop H. So again, I'm going to pick some point, pick that point. So we loop around clockwise. Again, we're going opposite the direction of the assumed current, so we're going to assume that's plus. In terms of voltage, we're going to rise this direction. We're going to decrease. From left to right, we would increase the voltage. From right to left, we would decrease the voltage. So it's I4 times 2. Okay, come down here. We're going in the same direction as the current. So we have minus I5 times 1. And then we come over here. We're going in the same direction as the assumed current, so it's negative I6 times 6. That equals 0. So we have 3 voltage equations, loop equations. The unknowns are the currents. And likewise, we have 3 junction rules. And the next thing we need to do is to put it in a matrix form. How do we do that? Well, in this case, what we would do is we would, I'm going to move the coefficients to the front. I'm going to move this 12 to the other side. And I'll just keep them negative. So you'll have negative 3 I1 minus I3 minus 2 I4 is equal to negative 12. So just rearrange that. The second equation, the 4 volts will go to the other side and become negative. I'll have negative I2, and I've got 2 components. I've got 5 plus 3, this resistor and that resistor, so we just add those resistors together. Plus, I'm going to put this one next because it's numerically the next current, times 1, and then plus 1 times I5 is equal to negative 4. Okay, so that's, let me draw some boxes around these things. Got that, got that. And then we have this one. So or we have 4, 5, and 6. And we have no voltage because there's no battery in that loop. So we have 2I4 minus 1I5 minus 6I6 is equal to 0. And what we're ultimately wanting to do is come up with a matrix. And let me just show you how this is going to look. We're going to have all the I1 terms in this column, I2, I3, all the coefficients, I4, I5, I6, and then on the other side, we're going to have the voltage, the constant. So it doesn't matter what order we do these in, so let's do these first. So we've got negative 3 I1 minus 1 I3 minus 2 I4 is equal to negative 12. Okay, so that's that one. Then we come down here, we have 8, 5 plus 3 is 8, negative 8 because we have a negative sign, plus 1 I3 plus 1 I5 is equal to negative 4. Okay, this next one is we have 2 I4 minus 1 I5 minus 6 I6 is equal to 0. Okay, let's just take these, and I'm going to copy these so we can see them. So let's group those together. Copy it. Okay, I'm going to add a page, paste in the values. So those are my other 3 equations. So let's put those into my matrix. So we have negative 1 I1 plus 1 I4 plus 1 I6 is equal to 0. Here we have 1, 2, and 3. So we have positive 1, minus 1, minus 1. Those are the coefficients in front of those. And the final one is 3, 4, and 5. And we have 1, minus 1, minus 1, 0. I forgot the 0 here. So 4 out of the 6 equations have zeros on the left-hand side. These are the voltages. That's what drives the whole thing. And then we can put zeros in for all the other ones, just to make sure we have everything taken care of. So everything lines up. We can see this well. So what it basically is we have 6 equations and 6 unknowns. And if we tried to solve this using other methods, it would be very difficult. So now that we have this matrix, what we're going to do is we're going to call this the A matrix, and we'll call this the B matrix. And to solve for the solution, so that the solution matrix for the current is going to be, well, let's go back. What we're basically doing here is you have a matrix A, which is made up of these coefficients, and we multiply it by the current matrix, which is made up of these currents, and that equals the voltage matrix. So we're going to take the inverse of the A matrix and multiply it. So we're going to take A inverse, and we're going to multiply it by A, and then the current matrix, and on the right-hand side we'll have the inverse matrix of A times B. So I'm just multiplying both sides by A inverse. This goes to what's called the identity matrix, which means it just like, basically we're going to, that's like multiplying the matrix by 1, and so our current matrix is just the inverse of A times B. And we can do that in our calculator. So let me turn the light in so I can see my calculator. So you may have done this before. I have to remember how to do this. So you go to the matrix and you go to Edit, and we choose Matrix A is a 5 by 5 matrix, because it's 5 rows with 5 columns, and then we start putting the numbers in. And it goes sideways. Actually, it's a 6 by 6 matrix. So let me fix that. Go back up, 6 by 6. Okay. -3, 0, -1, -2, 0, 0. Okay, then you go to the next row. 0, -8, 1, 0, 1, 0. Go to the next. 0, 0, 0, 2, -1, -6, -1, 0, 0. 1, 0, 1, and the next row, which is 1, -1, -1, 0, 0, 0. And you go to the final row, 0, 0, 1, -1, -1, 0. Okay, so that is the A matrix. Then we go back to the matrix thing, and we go to Edit again, and we go down to Matrix B, and we push Enter. And right, mine says 3 by 1, but I have a 6 by 1. It has 6 elements in a column. And my numbers are -12, -4, 0, 0, 0, 0. Okay, so I have these matrices entered in my calculator. And then all we have to do is go to the main screen, and we go again back to Matrix, and instead of going to Edit, we just go to the names, which is what comes up by default, and we pick 1, which is the A matrix, and then you do the inverse x to the -1 power. In this case, that's taking the reciprocal, but we're going to use the same thing to take the inverse of the matrix. So you'll have A in brackets with a raised -1. And then we're going to multiply that by the B matrix. So we go back to the matrix thing, and we go down to 2, push Enter. So what we end up with in the calculator, we see on the screen, it'll have A to the -1 and then B. So that's what we're doing right there. We've entered all the data, 6 by 6 matrix, so 6 by 1 matrix. And when we get that, we're going to end up with a 6 by 1 matrix, which will be the solutions, will be the currents. And we're going to have 6 entries. And what I get, I'm going to round these off, are 2.3, 0.69, 1.62, 1.72, -0.1, 0, and positive 0.59. So those are the 6 unknown currents. So now we're going to go back, and we're going to pick one of these drawings. Probably this one might be, well, let's just take the original drawing here. Let me select everything. Make that into a group. And then once it's done its thing, we'll copy it. Copy. We'll go to the page after our solution. So there's our original thing. So let's put the answers in here. So this I1 current is 2.3. I2 is equal to 0.69. I3 is equal to 1.62. I4 is equal to 1.72. I5 is equal to -0.10. and I6 is equal to 0.59. So because this is negative, the current is actually flowing in this direction. All the other ones are correct because they're positive. So what happens is 2.3 amps comes in here. We have 0.69 leaving here and 1.62. These added together should equal that. It's within 100, so it's close. So these are amps. Let's try these in here. Amps, amps, amps. So in this junction, we have 1.62 coming in. Instead of going down, we actually have it going up here. 1.62 plus 0.1 is going to be 1.72, so that works out right. Down here we have 0.69 amps. This thing, amps come around here, so this is 0.69. So that's coming in. Coming out is 0.59, and coming out is 0.1. So that's because 0.69 comes in, 0.69 goes out. So that's balanced. So you can see they're all balanced. This one would also be true. Here we have 0.59 going in. We have 1.72 going in here. So coming out has to be the sum of those two, which is 2.3 amps. So you see it all makes sense. And if we were to go back and calculate the voltage drops across each one of these things, we'd find out that the total voltage around the loop would be equal to 0. So let's just do one of these. Let's do this loop here. So if I add the voltage drop across here, the voltage drop across there, and the voltage drop across there, I should get 12 volts. So the voltage, again, is current times resistance. So let's do this. So we're going to have 2.3 amps times 3 ohms. That's the voltage drop across this resistor. Then we'll have 1.62 amps times 1 ohm. That's the voltage drop across that resistor. And then we have 1.72 amps times 2 ohms. And we put all that together. 2.3 times 3 plus 1.62 times 1 plus 1.72 times 2 is 11.96 volts, which is close to 12. Okay, so that one worked. Why don't we just do the other ones if you're interested. So we're going to go through this loop. So you'll have 0.69 amps times 5 ohms. What we're going to do is we're going to add all these, and this should go to 0. So we're going to have an increase of 4 volts. So this is a decrease. So we're going to have a decrease across this resistor. We're going to have an increase across the battery. We'll have a decrease across this. So it'll be negative 0.69 amps times 3 ohms. And we have another subtraction because the direction of this current is in the direction of the loop. So it's going to be 0.10, so it's negative 0.10 amps times 1 ohm. And then finally, this way we actually have a voltage rise because we're going the opposite direction. So that's going to be plus 1.62 amps times 1 ohm. And that should be approximately equal to 0. So negative 0.69 times 5 plus 4 minus 0.69 times 3 minus 0.1 times 1 plus 1.62 times 1 is 0. So we get exactly 0 volts. Now over here, if I had subtracted, these would have all been negative, and then I would have added the 12 volts, and I would have gotten basically 0.04 volts, which rounds off to 0. Okay, and then the final loop is the bottom loop here, but we don't have that many things in it. So we have voltage drop across this resistor, so it's going to be I6, which is 0.59 amps times the resistance, 6 ohms. Up here we have a voltage rise because the current's going from right to left. So you'll have a drop in this direction, so you'll have a rise in the other direction. So this one should be negative. It's because it's going to be positive, so we have plus 1.72 amps times 2 ohms. And again, here the current is going up. The actual current's going up, and we're going opposite that, so we're going to have plus 0.10 amps times 1 ohm. If we do that, 0.59, actually negative 0.59 times 6 plus 1.72 times 2 plus 0.1 times 1 is 0. 0 volts. So you can see they've all worked out correctly, that the loops work out correctly, and we've already done the amps. So every equation is satisfied. So it looks kind of daunting at first, but it really is. It's just a matter of keeping things, keeping track of everything. So let's review what we did. We identify, or we write on the diagram, the currents. At each junction we're going to have currents coming in and currents going out. And so I assumed that these currents are going in the direction shown here. Later on we find out that I5 is negative, therefore it's really going upward, but you don't know that until you run the problem. So we ended up with 3 current. We looked at 3 nodes, this one, and that one. Or we could have picked this one as well, it doesn't matter. We just picked 3 until we take into account all the currents that are involved. So these 3 current loop, these 3 junction rules cover every current. Then we do a loops, and we do the loops so that we include every element in this. So we could have done this is one loop, this is one loop, and then the whole outside thing is a loop. That would also include everything. So there's more than one choice in terms of the loops. But we needed 3 loops because we have 6 unknown currents, and we had 3 equations that we got from the current law, or the junction law, and so we need 3 more equations, so we have 3 loops. The loops, we sum the voltages. So we have voltage rises from the batteries. We have voltage drops across the resistors if the current is in the same direction as we're moving around the loop. If we're moving opposite, for example, here, this one, the current is going this way and the loop is going the other way. So actually, in this case, we have voltage rise across the resistor because of the direction that we're doing the loop. So we came up with 3 equations for the loops, loop F, loop G, and loop H. That gave us 6 equations and 6 unknowns, which these were the 3 junction equations, the 3 the 3 here were the 3 loop equations, and then you set it up as a matrix. So you rearrange them where there is no variable involved, you put a 0, and when there is a coefficient in front of the variable, you put the coefficients. The voltages, the batteries end up being on the right-hand side of the equation. So basically what we're doing here is taking this A matrix, multiplying by the unknown voltage, or the unknown current matrix, and getting a voltage matrix on the other side. So you enter that into your calculator. This is your matrix A, this is your matrix B. You write those in, and then to take the inverse of A, you do A with a little -1 sign as the exponent times B. That gave us the currents. That was the solution. It was pretty easy, and then we put them on our diagram. We guessed one that was in the wrong direction because we got a negative result right here. So instead of coming down, it is actually going up. And then we verified that all these things were correct by looking at the summing the currents into the 4 junctions, and they ended up being equal to 0. And then we looked at the summation of the voltage drops and rises around a loop, each of the 3 loops that we did, and they all ended up being either 0 or very close to 0. And so that confirmed that our answer was correct.